Hi, in this video, I'll discuss why use Julia for scientific computing. This is a video that I prepared as part of preparation for a presentation in an Indonesian workshop, a general workshop on sciences held in August 2022. But I kind of enjoyed preparing it, so I thought I might as well put it up on YouTube as well. So why use Julia for scientific computing? About me, I'm at the University of Queensland. I'm also a consultant at a very small firm, which we call Accumulation Point. Some of my main projects include the Safe Blues project. Links are in the description of this video. That's a project that deals with transmission of virus-like tokens for purposes of privacy-preserving epidemic surveillance. There is the Mathematical Engineering of Deep Learning book draft, which is online, with chapters appearing online as time progresses. This is a book that aims to present the story of deep learning actually without any computer code, but rather from a mathematical notation perspective. And also have a look at my Statistics with Julia book. Just Google Statistics with Julia. This book co-authored with Hayden Clock has statistics from the ground up using Julia code at a very simple level. So scientific computing, what is scientific computing? It's a very broad term. It might include statistics, anything that has to do with statistics or computational statistics, or more generally data science, processing of data, analyzing data, data-based models, etc. And machine learning, deep learning, artificial intelligence, that is part of scientific computing as well. But then you get to more model-specific things, such as simulation modeling, and that can mean a variety of things. It can mean Monte Carlo simulations, or deterministic simulations, or epidemic simulations, or micro simulations, or macro simulations, or weather simulations, etc. And in general, mathematical modeling and computing. Now, in scientific computing, we also have computational engineering mathematics, the now classic fields of signal processing, control and such, and a variety of domain-specific areas, fluid mechanics, physical simulations, geology, genetics, the list goes on. Scientific computing also involves education for all of these above fields, and there is more. So what do you use? Scientific computing, you need a computer. The computer needs to be programmed in one way or another. What language do you use or have used? So here is some partial list of languages where in the end, I put the Julia language, and that's the focus of this talk. But let's just kind of get a bit of an overview. So you've got some low-level languages, C or C++, certainly considered low-level languages, or the older Fortran, and quite a lot of things are done in these languages. I've done myself quite a lot of simulations in C and C++, and it's a bit difficult because you're chasing pointers and you need to compile every time, but it can actually be quite efficient in terms of computation if you know what you're doing. You've also got modern low-level alternatives. The Go language, which existed for about a decade, a bit more, in the Rust language. So these are still languages that are considered low level in the sense that you're programming things that are quite close to the machine, but they're just more modern. And of course, there's a new version of C++ coming out as well. Quite similarly, you've got languages such as Java, which has already existed for about 30 years, nearly, with the Java virtual machine, and it's used throughout enterprise companies, etc. There is Swift, developed by Apple, but also open source. So that is a language that feels kind of like Java. And C# is the Microsofty Java. You might say that Java, Swift, and C# are still quite low-level languages. They just offer programmatically things that are sometimes a bit easier than C, C++, or Fortran. For example, they have garbage collected memory allocation, whereas the real low-level languages don't. Then you move to something completely different, and many of you might have grown up in the world of scientific computing with MATLAB. MATLAB is easy. You put a matrix, and that's the basic entity in MATLAB, and it works. You can multiply matrices, invert them, you QR decompositions, singular value decompositions, do a variety of things, and MATLAB kind of works. But it's very interpreted, meaning it is interpreted. It is slow, as opposed to compiled, where 1, 2, 3 are compiled. It's also proprietary. You need to pay for a license, and that might be okay if you're part of a big institution, but then when you move on and do something small by yourself, that's not possible, and it's harder to distribute our stuff. So there is a 3 version of MATLAB called Octave, but it's not as powerful as MATLAB. MATLAB still dominates the electrical engineering mathematics world in many ways, although Python is starting to take over on that domain. And then you've got the language of R. So R, the R programming language, evolved as the free version of the S programming language. And R is very powerful for statistics, for data analysis. It's useful for these things. And this is a common language that you would use if your scientific computing is statistical in nature. There are tens of thousands of packages for R, and almost anything that you'd want to do in statistics has been done in R. But it's slow, and it's not very versatile, and it's really focused on statistics. You won't find a whole bunch of general numerical mathematics in R. It's certainly not the tool that somebody would use initially. And then we get to the world's most popular language, at least in the year 2022 now, and that is Python. So Python can do pretty much anything. You can create a backend for a website. You can do text processing. And with packages such as NumPy or scikit-learn, or the machine learning packages such as PyTorch or TensorFlow, you can do machine learning as well. You have pandas. Python does everything. It's easy to use, but it's not designed per se for scientific computing. It's a much more versatile language. And it's, in a sense, kind of old. It's an interpreted language that has existed for over 40 years, and it keeps evolving and getting better and better. And it has a huge, wonderful user base. But it's anachronistic in many ways. Now, Python is taking over MATLAB in many ways in university introductory courses for scientific computing and engineering mathematics, but it's not naturally designed for scientific computing. Now, if you get to specific domains, very popular in physics, mathematics, sometimes in financial mathematics, then Mathematica is great, and there is also Maple, which is somewhat similar. So these languages are well known for their symbolic ability, for their ability to manipulate algebraic expressions, implement computer algebra systems, and they do a great job in that. Mathematica, which is now called the Wolfram language, actually, does a whole lot. But again, both are proprietary, and they are not the type of thing that you would use for fast computations, where you actually need to simulate a lot of things. But both are very powerful. And some people actually use web development for scientific computing. So in the world of web development, JavaScript is the main language, but you can have, by the way, JavaScript running both in the web browser and in your backend, or sometimes the backend might be on the server, might be with Python. It's not the standard way, but there is a non-negligible amount of people that actually use JavaScript for scientific computing. It's certainly not designed for that. And then we get to the focus of this talk, number 9, Julia. So let's speak about Julia. So what is Julia? Julia is a programming language that's existed for about 10, 12 years, depending how you count. So it's now certainly way in its second decade. And it started with a focus on scientific computing. It's trying to be a more general language as well, but it really is a scientific computing language. So why use Julia for scientific computing? So this is my single slide answer. In general, you want to do things fast. fast means. Quickly, it means you can move on to the next thing, or it means that with a given time constraint of actual clock time, you start in October and you finish in January the next year, in actual clock time, then you've delivered your product, whatever it is, quicker. And one way to measure this speed is to take this vertical axis and speak about development speed, and take this horizontal axis and speak about run speed. Now, of course, if the actual thing that you're computing takes only a couple of hours, you might say, well, run speed is maybe not so important, or maybe it's even a couple of minutes. But actually, fast run speed allows you to run again and try again and refactor and tweak and try different parameters and improve. Whereas if you need to wait for hours and days for computation to finish, then run speed requires much more planning from your perspective, etc. Now, in general, there's this Pareto optimal frontier where most people would agree that if what you're looking for is run speed, then maybe go to C, C++, or Go or Fortran here on the bottom right. And these languages, it might take a bit longer to code, well, take significantly longer, and debug and test, but they will run fast. Contrary, when you want to do something quickly and you want to experiment and you want to change algorithms and you want to try different variations, you can go to Python with NumPy or scikit-learn, etc., or use MATLAB or R or Mathematica or another high-level language. And these ones on the top left are more of the scripting nature. Now, actually, what happens in practice is that when people deliver solutions, then they actually use kind of both. They use this bottom right to make things fast and efficient, and they use the top left languages to actually code, script, use the front end, etc. In fact, many R packages have C code or Fortran code that runs under the hood, because if the code would be written in R, it just won't run fast enough. It won't be efficient. And similarly for Python, NumPy in Python is developed with a low-level language. Okay, so the actual code that's happening under the hood is run in low-level languages. So one actually requires two languages to deliver a solution often. Even if you're just working here, you're actually using stuff that was written here, and it's hard for you to see what you're using there. Now, Julia, this 10-year-old language, actually breaks this frontier. It moves beyond the Pareto optimal frontier that appeared prior to its existence. And it delivers speed that is in many ways comparable to C, C++, Go, Fortran, and ease of use, which is very much comparable to Python, MATLAB, or Mathematica. In fact, I would argue that it is up here. It is a bit faster than C, C++, Go, Fortran if you do things correctly, and it's certainly easier to use than some of these. However, there are also still some deficiencies in the sense that it's not as popular, and having a language with a low user base implies that it's harder to find questions for answers on the web, etc. But these things have changed. Julia is already quite a contender. So how does Julia do this? Well, why is Julia miraculous? Well, it's not miraculous. It's simply the language that arrived at the right time for the right task, and that's scientific computing at about 2010. So in terms of syntax, Julia syntax really takes the best of Python syntax, MATLAB syntax for matrices and such, and R syntax for the way functions are called with parameters. However, it uses computer science paradigms from the past 10 years, not from 40 years ago. So it doesn't carry all this baggage. So as a starting point, when Julia was started to be developed at about 2009, the starting position was good. There was already all this knowledge in humanity. And I think the Julia developers did a great job in the final product, or the product that exists now, which is Julia 1.7, beyond Julia 1.0. Now, Julia has inbuilt package management and out-of-the-box scientific computing, two different things. So inbuilt package management actually means that it's standardized. It's very easy to install packages in Julia. It's also easy to install packages in Python or R. However, it's just done in a more modern way in Julia. The package management is kind of like Conda, but which is a Python package manager, really. But it's just more unified than other languages. Certainly for a open source free language. I mean, package managers in MATLAB and Mathematica are fine, but there aren't so many packages because these languages are proprietary. And it comes with out-of-the-box features for scientific computing. So with Julia, you get matrix multiplication and linear algebra built in. You just need to add that library using linear algebra. You get some basic statistical operations also built in. You get basic mathematical constructs such as square roots, factorials, and a few other special but not very special functions built in. And the other things, you install packages as you do in Python and R. In a sense, it kind of follows the R paradigm where a lot of statistical things are built in. Okay. You get a clean dynamically typed language. So the dynamically typed is important. Julia has types, and types take a more central role than they do in a language like Python or really R, and certainly MATLAB. So the fact that there are types in a somewhat similar way to the way you would use types in a low-level language like C or C++ or Java, perhaps, allows the language to bind things in an efficient manner and run fast. However, it also is not as stringent as the lower level languages in terms of defining types. So when you start scripting with Julia, you actually don't need to worry about types. And later on, you think more about types. Now, one thing that shows that this language is kind of clean and mature is that most of Julia, and I'm not talking about Julia packages, the actual Julia language is written in Julia. But more importantly, almost all of the Julia packages are actually written in Julia. So when you use a Julia package for carrying something out, generalized linear models, or lasso, or numerical computations of sorts, or ODE solutions, that code will be written in Julia, and you can actually inspect it. You often don't need to inspect it because you just use a package, but the fact that there is one language under the hood that's running everything is very efficient. And it all becomes very efficient because the language actually has a compiler which compiles functions dynamically down to LLVM. LLVM, low-level virtual machine, is an intermediate assembly-like language, also used by technologies such as Swift and Go and some C compilers. But Julia compiles things down to LLVM and then uses the state-of-the-art LLVM compiler at any given time to compile this LLVM down to assembly language on whatever computer you run. So LLVM was not available when Python was developed and MATLAB was developed and R was developed. Julia allows for strong metaprogramming support, and that means that people have built languages on top of Julia. Languages for integer programming, that's for mathematical optimization in the context of operations research. Languages for describing statistical models, and other sub-languages that use metaprogramming support. So this is macros and such. And of course, the language is open source, unlike MATLAB and Mathematica. Now, in the Julia community, performance, speed, run speed, and simplicity is kind of an inherent value, especially performance, but also simplicity because things are nice and clean. So code in Julia in general is efficient. But still, when you go and write code, if you're a user and doing some scripts, you don't need to worry about these things too much. You can just write your code. But then if you're actually going to want it to run fast, super fast, then you can take another pass on the code, optimize it, and improve it. And the Julia community deals with that a lot. And in general, the community is focused on the breadth of scientific computing, but it's not a huge community at this point in time. So you actually, almost any area of scientific computing has been touched or has several people around the world working on it using Julia. And that's, for example, it's different in languages such as Go or Rust or Swift, where people generally don't use those languages for scientific computing. So here's some more reasons to use Julia for your next project. So you can do matrix algebra, mathematics, and statistics with Julia built in. Automatic differentiation, so differentiable programming. So taking some function that you've written and evaluating its derivative or Jacobian or gradient or Hessian at a given point, if that's appropriate, is almost built in. There are plugin packages, but these packages interface with the Julia compiler in an efficient way. So Julia is an advanced language for automatic differentiation. So that automatic differentiation is what's used in backpropagation and deep learning, but it's used way beyond that in many areas of scientific computing. If you want to take a derivative of something, it is there. Nearly 10,000 packages to date that cover the breadth of scientific computing. Strong data frame support. Data frames are Excel spreadsheet looking data structures, so heterogeneous data structures with columns and rows, like pandas in Python or data frames in R. And Julia has a great data frames package. And there are multiple plotting and visualization packages, specifically the one that has become the standards, plots.jl is great. There's also a very nice package, Mackie, and Julia does a good job of this. Now, I wouldn't have made this video before 2020. I've been using Julia from around 2017, but it's really around 2020 that the ecosystem and language reached some level of maturity. Around 2020, the language hit. Just before that, Julia 1.0, so things have stabilized. The package manager stabilized. The way things work has kind of stabilized, and the language is now quite mature and easy to use. And there's a great community of Julia users. It's not too large, so not every third person around the world, not at all, but it's big enough to have interest in almost any aspect of science. And if you're now posing questions in Julia community, and perhaps in Stack Overflow, but typically in Discourse or in the Julia Slack, the community will provide quick answers. It's easy to integrate Julia with GPUs as well, with graphical processing units. In a sense, it's much more natural than doing so with, say, Python. Now, a final reason to use Julia is that if you're working in your field, whatever that is, agriculture, epidemiology, some other form of science, you can innovate in your field with Julia by actually doing things with Julia that would have taken longer with another setup like R or Python or MATLAB. And there might be some innovation in that activity in its own right, because you might need to develop a Julia package or some supporting code that has not existed in that area previously. So entering a mature language, but not super popular language, is quite an interesting thing to do. So here are just a few things that you might not like. And of course, we need to state these two. So many people are put off by array indexing that starts at 1 and not at 0, but that the world really differs on that. Some people find array indexing starting at 0, Python programmers, JavaScript programmers, C, C++, Java, Swift programmers. Whereas if you come from MATLAB or R, array indexing starting at 1 is natural. And mathematically, there's an argument for array indexing to start either at 1 or 0, and there's not really a correct answer. Anyway, in Julia, it's at 1. 2 is a big one. As of today, 2022, when you install Julia and you plot something, you create some data, and then you hit plot, you might wait for that first plot for a couple of seconds. A couple of seconds, not a couple of milliseconds, a couple of seconds. The reason is that Julia is going to compile things for the plot package for the first time. Afterwards, it will be quicker. So while the language is fast, it is not fully interpreted. It's actually compiled as you type. Well, as you type and submit things to the Julia kernel, and hence there is some latency in the language. Now, this is something you might not like, but you might very much like. I have mixed feelings about it. The Julia community actually involves many very smart people. Once you join the Julia community and you start discussing with people that are doing stuff in Julia, you'll say, oh, there's like so much knowledge in this community. People from top institutions, top universities doing very innovative things. That's not necessarily a bad thing, but you might just feel, I feel like that sometimes, wow, just a bit overwhelmed by all this knowledge around you. Now, if you're used to an IDE, an integrated development environment, such as RStudio, or maybe use Spider or something like that for Python and you really like it, or just MATLAB, for example, the Julia experience will not fully compete with that. With VS Code, you have a good IDE for Julia, so you can inspect data and you can debug a bit and you can look at plots, etc. However, there's not an integrated RDE like RStudio that's fully focused for Julia. It's part of Visual Studio Code, a very popular editor. Now, some people are put off by the fact that Julia is not object-oriented. So in contrast to Python, C++, Java, Swift, where you have an object, and the object has methods and variables, and then you can have an object and you can do dot, and you'll see the methods actually. You'll go for the methods. Julia is more functional in the sense that there are functions, and a function can actually have multiple methods, and the big thing with Julia is multiple dispatch. So it's a different paradigm. However, I would argue, and many have argued before me, that for scientific programming, object-oriented code is actually not the most natural, or object-oriented design is not the most natural paradigm to use. Look, for example, at NumPy and see in NumPy, ask yourself, why are some things functions in NumPy and some things are standalone functions, some things methods? Well, because it's trying to be object-oriented, but often you have operations that require two or more objects, and then it's actually not natural to put them as methods of a single object. There is an inheritance of a type system, though. There is type hierarchy in Julia. So you can do all of these things in a very structured way. It's just not your standard small talk C++, Java, C#, Python way. Now, some people are put off by deployment in the fact that if you actually want to make lean, quick, standalone applications, compile them and throw them away, you can't do that very easily with Julia. But for scientific computing, that's not a major thing because you're typically not deploying your product to run on a server someplace else or something like that. We have made web servers that have Julia in the back end and present things to the front end, but that is still not the standard use with Julia. Now, if your focus is primarily deep learning, specifically deep learning, maybe some sorts of ML or AI in general, but specifically deep learning in the TensorFlow or PyTorch sense, then Julia is still not in the same state of the art as Python is. So there are great deep learning libraries in Julia, but a lot of them are actually focused on very specific domains of what's called scientific machine learning. So yes, you can do image classification and segmentation, and you can do quite a lot of things with deep learning, but it's just not as popular as Python. So it's still not state of the art, but it will be. And it's still not the language of hardcore statisticians. If you're a seasoned statistician and you use dozens or tens of dozens of packages for time series, for all kinds of multivariate analysis, for things like that, some of these things exist in the Julia ecosystem, but some still don't. There is nice interoperability, though, between Julia and Python and R. And the ninth reason that you might not like Julia is, well, you tell people, hey, I'm working in Julia, and they might tell you, what is it? What is Julia? But then again, you can ask yourself, are you a person that wants to work in what everybody uses, or do you want to kind of innovate and try new things? So where to start? So let's say that you've listened to this video up to now and you said, okay, I'm going to give Julia a go. Of course, you might be doing different kinds of things. Well, here's some things that you might start. And this is a very biased list. Well, it's biased because a few of my co-creations are on this list as well. So one thing you can do quite easily is install Julia. Recommended that you install Jupyter as well. That's iJulia. Okay. And maybe VS Code if you like an IDE. So install Julia for VS Code. There'll be a link to this video on how to install, but there are many other installation videos as well. And it's not hard. So you can do it on Mac, Windows, or Linux. And then spend a weekend or an evening for your extended Hello World. A simple Hello World is not hard. Just println Hello World, enter. But try to do a few basic things and ask yourself, how do you do this? How do you plot? How do you generate random numbers? How do you do a loop or a conditional statement or even define a function? Now you can join the Julia community. And if you just Google Julia Slack, there's actually a Julia Slack community where you can join. And there are many sub-channels in Slack. And then if you have more time that you want to invest, you might follow this great course from MIT, Computational Thinking. So I'll put a link to these videos, YouTube videos, or a course that we teach at the University of Queensland, and that's Programming for Mathematicians. Both use Julia, and there are about 150 other courses throughout the world that use Julia, but this is, again, that's a biased list. Now, you can follow JuliaCon talks. So every year there's a conference called JuliaCon. All the talks are on YouTube. Again, I'm biased. There's a 3-hour workshop of mine from 2021, Statistics with Julia from the Ground Up. It's also good if your focus is scientific computing, not of the statistics type. But there are many, 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 many other talks, very good talks. Some of them are workshops, tutorials, and some are more domain specific. So just look at YouTube. I do warn you not to spend too much time on Julia YouTube videos that are perhaps older than 2018, or at least not in the detail, because some major things have changed in the Julia syntax as Julia was leading up to 1.0. But as I said, the language has matured. And what's the next step? Well, get your first research project going. Start simple. Maybe you just need to make a little plot or analyze some data or do some linear regression or fit a model. Or maybe you want to do a bit of a simulation with some nested loops or solve an ODE. Put that in your first research project. You don't have to go with the language fully yet, but see how that works. Or alternatively, if you're a lecturer like me, or you teach, or maybe you're a teacher's aide, then just use Julia in your classroom. Maybe first as a demonstration, you can do things beforehand and show, or you can do that live. Or you can follow the track that I've done in the last 5 years, and that's use Julia throughout my teaching. And of course, there are Julia-based books. I'm showing just 2 here. One of my favorites here is Algorithms for Optimization. This is a great book, and it actually has all the pseudocode. It's not pseudo, it's just Julia code, because Julia code looks like pseudocode in a sense. It's very readable. And there's a book that I co-authored, Statistics with Julia, which will teach you statistics kind of from start to end, all with Julia examples. And you can get the code for both of these books and others and try it. So these are some of the places you can start. And of course, there are many other places and things to do. And I'll finish with that and hope you enjoy. Good luck. Bye-bye.